All right, we want to give an example of a bounded set C of measure 0 such that the integral of the indicator function does not exist. All right, so there's sort of a standard example for this. So what we're going to do, we're going to let C be all the rational numbers that lie between 0 and 1. C is bounded because it's a subset of the interval from 0 to 1. We want to prove that it has to measure 0. And I think this argument was given in the textbook. But given epsilon greater than, index C by, we'll call these Qi. I will go from 1 to infinity. The rational numbers are a countable set, and so the rational numbers in the closed interval from 0 to 1 is a countable set. So we've got this so C is a countable set, so we can list out all the values. So we've got Q1, Q2, Q3, all the way off to infinity. So index C by using this notation, and given epsilon greater than 0, let so that ui be an interval containing Qi with length 2 to the minus I minus 1. Then what we do is the sum from I equals 1 to infinity of the volumes of the ui's. So this is going to be the sum from I equals 1 to infinity of 2 to the minus I minus 1. And so this is going to be, no, we need an epsilon here, epsilon. So this is going to be epsilon here. So if we sum this up, we're going to get, let's see here, 2 to the, no, we just need minus I. What am I talking about? Because 2 to the minus 1 is 1/2, a fourth, an eighth. Yes, this will converge to 1. So the sum of 2 to the minus I, sum from 1 to infinity, is going to be 1. So this sum is going to be epsilon. All right. So given any epsilon greater than 0, we can cover, well, yeah, we should state that. And C is contained in the union from I equals 1 to infinity of ui. Because Qi is contained in ui, so any element of C is contained in some ui. So the set C is contained in the union of the ui's. Okay, so thus the measure of C is 0. This is how I write the measure of a set. This notation means the measure of C is 0, or C is a set of measure 0. Because the definition to be a set of measure 0 means that you need to have a cover of the set such that the sum of the volumes of the sets in the cover is less than epsilon. Oh, well, okay, so if we need less than that, okay. But this needs to be true for any epsilon. And that's what we have here, so we've got, it's a set of measure 0. Okay, now we need the integral to not exist. All right. Now, given any partition P of the integral over A So let's just call A interval from 0 to 1. I guess they want you to choose that. So if you've got a partition of this, what is going to be the lower sum of chi c given P? Well, given any particular here, let's write it like this. So we've got partition, any u in P contains rational and irrational points right? Because that's a fact. Any closed interval that has positive length has a rational number and an irrational number. Rationals and irrationals are dense in the reals. Have we talked about that in this course? In this textbook? We should have. It's a really important fact. I'm going to assume that we've talked about it and finish the rest of this, and then maybe come back and talk about how I would prove it if we didn't know that. So any closed interval in this partition, because this partition, like, we're taking intervals of positive length. So a closed interval from A to B, where A is strictly less than B. So any such interval will contain both a rational and an irrational point. So the rational point will be in C. The irrational point will not be in C. So what this means is that if we look at the lower sum of chi c p, now given any set u, if we take, to compute this lower sum, then for any set in this partition P, you need to take the infimum over all points. And we know that it contains an irrational, we know that any set in this partition contains an irrational point, and that irrational point is not in C, because C contains only rational points. And so there's a point in this set where the function chi c takes on the value 0, because the point is not in C. So what that means is that infimum term, the infimum over all points in that set of chi c of that point, will be 0, because you'll always be able to find a point where it takes on the value 0, and the function doesn't take on any values lower than 0, so the infimum is 0. Okay, so, but then that means that the this lower sum has to equal 0, because what you're doing when you compute this lower sum is you sum over all sets in the partition. Let's write that out. Sum over all sets u in this partition P, we take the minimum over u of chi c times volume of u. And like I said, the minimum of chi c over u is 0. So this is just the sum of 0 times the volume of u. And so that's just going to be 0. And the upper sum of chi c p is going to be similarly the sum over all u and p, but now we take the maximum over u chi c times the volume of u. But now the maximum, for any set u in P, you're going to have a rational point, and that rational point it's in the rationals, and it's in the set u, which is a subset of the interval 0, 1. So it will take on the value 1 there. So the maximum value is 1, and it won't take on any values greater than 1, so the supremum is 1. So this is precisely the sum for all u and p of the volume of u, and with this being a partition, this is just the length of the interval, which is the length from 0 to 1, which is 1. Okay. So so the lower sum is always 0 and the upper sum is always 1, and this holds for any partition. So if we take the supremum of the lower sums, this is also going to be 0. Because taking the because each lower sum is 0, and so if you take the supremum of a bunch of zeros, you get 0. This is strictly less than 1, which is the infimum of the upper sum of chi c p. So the supremum of the lower sums is not equal to the infimum of the lower sums, and hence the integral chi c does not exist. All right, so that's the end of the exercise with the way that I've proven it. What else? What other options do we have? Because I use this thing that any interval contains both rational and irrational points. I don't know how much we've delved into the real numbers in this textbook, but let's think about it. So, what other tools do we have? We have that fact about was it points of discontinuity? Yeah, so you could use that instead if you wanted to. For a function is integrable, a bounded function is integrable if and only if the set of points at which is discontinuous has measure 0, I believe is the statement. Or maybe it's content 0, but it's one of those. And either of those is going to be false in this example, so you can use that. Maybe that would be a better way to do it. But I like the argument that I've given here. This is more standard analysis, but maybe for the purposes of the textbook, it's better to use that theorem. Well, and yeah, that theorem just came up in this section of the textbook, so maybe that's what they want you to use. But yeah, so the argument you use there is you look at this function chi c, and you choose any point in the interval from 0 to 1, and you choose any neighborhood about that point, and well, wait, no, that's using the same thing. That's using that you always have a point that's in the set and a point. Yeah, no, you really have to use that fact that rationals and irrationals are dense in the real lines. So this has to be something that has been discussed at this point. And I mean, I guess if you want to prove it, maybe there is some like even simpler example or argument that I'm not thinking of. But just the fact that the rationals and irrationals are dense in the real line, meaning that any closed interval of positive length will contain both rational and irrational numbers. That's a very standard result of analysis, and you can find that in like the first chapter, maybe the second. No, it's got maybe the second chapter, but almost certainly the first chapter of Baby Rudin, Principles of Mathematical Analysis by Walter Rudin. So if you haven't proven it up to this point, you can even just look at that textbook and just copy and paste the proof of that fact into here. It's because I'm so used to using that because it's such a standard result in analysis that you sort of just use it automatically. Because it's it's really important. But anyways, yeah. So we've done this exercise, and I, for one, am satisfied with this argument that we've given, and it's possible that this is something that's been talked about already in this textbook, and I'm just worrying over nothing. But anyways, I am content with this solution, and so we are done.